All right, in this lesson, we are going to talk about how to factor special cases. So this can save us a lot of time, especially when numbers get large. And so starting with a review on how to factor trinomials, whenever a is 1, so in the case of number 1 and 2, these factor very quickly. You're looking for the magic numbers. And so the two magic numbers are numbers that multiply to your last number, but add to your middle number. I like to organize it using the X. And so looking for two numbers that multiply to 12, but add to 8. Those numbers would be, if you want, you can make a factor table for 12, 1 and 12, 2 and 6, 3 and 4. And then the pair that adds to 8 is the 2 and 6. Okay, and so 2 and 6 multiply to 12, but add to 8. And so this quadratic factors to x plus 2 and x plus 6. To check your work, you can multiply that out. X plus 2 times x plus 6. And you would get x squared, 6x, 2x, 12. And then when you combine your like terms, you're kind of seeing those magic numbers. 2x plus 6x is the 8x. And so that gives us x squared plus 8x plus 12, which was our original quadratic. And so we know these are the correct factors. Okay, in this next example, we are looking for two numbers that multiply to negative 35, but add to 2. Okay, 7 and 5 will work to multiply to positive 35, to multiply to negative 35, but add to positive 2, the 5 would need to be negative. And so this factors to m plus 7, m minus 5. If this were a negative 2, we would have made the 7 negative and the 5 positive. All right, looking at number 3, this one's challenging, not only because a isn't 1, but also because these numbers are kind of large. And so it may take us a while to find the magic numbers. And so start with a times c, which is negative 140. And we're trying to find two numbers that add to 31. And so to make our list, just focus on the 140. Starting with 1 and 140, 2 and 70, 3, if you're not sure, do 140 divided by 3. Doesn't work. 140 divided by 4 is 35. And we're kind of back to some easier cases, 7 and 20. 8 doesn't work. 9 won't work. 10 will work. And then 11 doesn't work. 12 doesn't work. 13 doesn't work. And we're back to 14. Okay, and so these are all the numbers that multiply to 140, but keep in mind this is a negative 140. So one of these numbers will have to be negative, either the left side or the right side. And so we're looking for two numbers that subtract to give us 31. And so of course 1 and 140 won't work, 2 and 70 won't work, but 35 and 4 will work if the 4 is negative. Okay, and so now when you have those magic numbers, you can't just skip to your parentheses because we're trying to get a 10r squared. So what you do with those numbers is you split the middle, negative 4r plus 35r, either order, and then you are going to factor by grouping. So bring down your last term, bring down your first term, and you're looking for a GCF out of each pair. So looking at the first pair, both of those numbers are divisible by 2, and they both have an R. So 2R, and then when we actually do the division, we get 5R minus 2. Out of the second pair, we can divide both by a 7, a positive 7, which would leave us with a 5R minus 2. Now the goal is to have matching parentheses, which we do. That means we've done everything right. So 5R minus 2 is one of my factors, and 2R plus 7 is the other. The 2R plus 7 comes from what is outside. Okay, so in general, whenever A is 1, you can skip to just writing the parentheses after you find the magic numbers. When A isn't 1, you have to take the 2 extra steps of factor by grouping. This factor by grouping method will work all of the time. So if you want to use it for A equals 1, you can. If you want to use it on these special cases, you can. Except when the numbers are large, sometimes it could take you a while. And so there are some shortcuts that apply to special cases. The first case is the perfect square trinomials. And so I'm going to start with some easy examples where the shortcut isn't useful, but then we'll get to some harder examples like 4 where it absolutely is helpful. And so looking at number 1, A is 1, and so we're looking for 2 numbers that multiply to 9 but add to 6. Multiply to 9 but add to 6. Those numbers are 3 and 3, which tells you you're working with a perfect square trinomial. Whenever your magic numbers match, that means your factors are going to match. And so in this case, my factors would be R plus 3, R plus 3. And whenever they match, they typically rewrite it as R plus 3 squared, because that's R plus 3 times itself. And so these perfect square trinomials are always going to look like a parenthesis squared. Okay, for this next one, we're looking for 2 numbers that multiply to 144, but add to negative 24. Those numbers are negative 12 and negative 12. And so we could write this as k minus 12, k minus 12, but since they match, we're going to write it as k minus 12 squared. Okay, for this next example, we're looking for 2 numbers that multiply to 49, but add to 14. That's 7 and 7, and so t plus 7 squared. Okay, so for this next example, we could multiply 9 times 16, which is 144, and then find 2 numbers that multiply to 144 and add to negative 24, which is negative 12 and negative 12. But of course, this does not factor to a minus 12, a minus 12. That was this example up here. This is where a isn't 1. And so we would have to split the middle and factor by grouping. Okay, and so when we do that, we're still going to end up with matching factors. And so looking at our first pair, we could divide both of those by 3 and a. And that leaves behind a, or 3a, minus 4. Out of the second pair, the leader is negative, so GCF is negative, and those are both divisible by 4. So negative 4 is our GCF, and when we do that division, we get 3a minus 4. Our parentheses match, so 3a minus 4 is one of my factors, And then the other factor is also 3a minus 4. And so we can still write this as 3a minus 4 squared. Now here's the shortcut for working with perfect square trinomials. If you recognize that your first, let's look at this example since it's more interesting. If you recognize that your first and last term are perfect squares, 9 and 16, square root each one. So square root of 9a squared is just 3a. Square root of 16 is just 4. Okay, and then copy the sign of this middle term, which is minus, and this is going to be your repeated factor. So add parentheses and put a square. Okay, it's important to check that when you multiply these two, 3a and negative 4, you're going to get negative 12a. That should be half of your middle term, okay? If that's not the case, this was not a perfect square trinomial. Okay, so let's try this method here. We could square root first, square root the last. So t7, copy the sign, add your square. T plus 7 squared. Square root the first, you get r. Square root the last, you get 3. Copy the sign of the middle, squared. Okay, square root the first, square root the last, you get k. 12, copy the sign, add your parentheses, squared. So in each case, that's just a shortcut. It's not useful for 1 through 3, but for problems like number 4, where you have a other than 1, it does save you a lot of time. Okay, the other special case that you need to know is when you are missing your middle term. So on each of these examples, you're only seeing 2 terms because the middle term is missing. We have the squared term and the constant. Okay, and so that means my middle term, the m term, was 0. Okay, and so you're looking for 2 numbers in this case that multiply to negative 25, but add to 0. Okay, 5 or negative 5. That means these numbers have to match but have opposite signs in order to be adding to 0. It's a 0 pair. And so this time we can't write it as one factor. We have to write them both. One's positive, one's negative. Okay, and so notice in all of these examples, we had a middle term. We had a middle term because these were all trinomials. In these next set of examples, we don't have a middle term. Our middle term is 0. So here we have h squared plus 0h minus 81. And so we're looking for 2 numbers that multiply to negative 81, but add to 0. That would be 9 and negative 9. And so we have to write them both. H plus 9, H minus 9. Okay, here we're looking for 2 numbers that multiply to positive 49, but add to 0. Okay, and so as you try to come up with this list, a lot of people want to try to say 7 and negative 7, but those would multiply to negative 49, so that doesn't work. So then we try 7 and 7, but then those don't add to 0. Then we try negative 7 and negative 7, those don't work. They have to have opposite signs in order to add to 0, and then they have to have the same sign in order to multiply to a positive. And so this actually is not factorable. And the difference between this example and the other examples is the minus sign. Okay, and so this plus sign makes it not factorable. So that's why this is called difference of squares. Anytime you're working with a difference, a subtraction of two perfect squares, the shortcut for that is to square root the first, square root the last, write it twice, one with a minus, one with a plus. Okay, and so in this example, if we square root the first, we get m, square root the last, we get 5, one with the plus, one with the minus. Square root the first, we get h, square root the last, we get 9, one with the plus, one with the minus. And so that's really gonna help us here because a isn't 1. So square root the first, we get 5g, square root the last, we get 6. Okay, and so our factors are 5g plus 6 and 5g minus 6. That's saving us a ton of time of trying to figure out what 25 times 36 is and then find the magic numbers that multiply to that but add to 0. That's a big number. And so when they test this skill, they do use huge numbers. So as long as you have a perfect square minus a perfect square with that x squared there or g squared, whatever variable they're using, they could use any of your perfect squares. So 1, 4, 9, 16, 25, 36. And oftentimes they'll use numbers that like 100 so that you can't really factor this. So let's say it was 100 squared minus 9. This would factor to 10x minus 3 and 10x plus 3. Okay, so anytime you see two perfect squares with 0 in the middle, meaning the term is missing, you're going to have two factors that look the same, but one is a minus and one was a plus. When you have a trinomial that start and end with a perfect square, square root the first, square root the last, and copy the sign of the middle term. And then you're just going to have one factor with a square.